Let this mark the end of the Cybertronian Wars as we march forward to a new age of peace and happiness. Till all are one!
Till all are one! Till all are one!
You got the touch!
Till all are one!
Good day. This is the second in a series of videos designed to illustrate how to create predictive models which are simultaneously explicable and precise. As we mentioned in the first video, it is important to observe that there is a difference between mathematics and arithmetic. Mathematics is what tells you what arithmetic is salient and what arithmetic is superfluous. And thus, before even examining some of the code which will help us create these explicable models, one of the things that is important is to examine some of the underlying mathematical theory behind the computations that are made. The topic of this video has to do with variable standardization, and so we will examine what is typically meant by that. Then we will propose a different method of variable standardization and make an argument for its superiority. So, if you take any textbook on data science, one of the things that the authors will encourage the user to do is to standardize their variables when performing predictive analysis. And so when they say standardize, what do they mean? Well, what they mean is subtracting the mean of the variable and dividing by the standard deviation. Now, why would a person do such a thing? Well, there are a few reasons. One is that the new variables will have the same mean and variance, mean of 0, variance of 1. Moreover, the new variables will be unit-free. When you divide by the standard deviation, you will also be dividing by the units of that variable, and so in a certain sense, all of the resultant variables will be the same. That is to say, they will have all the same unit, which is to say, none at all. Moreover, there is an easy interpretation of the coefficients in linear combinations of the original variables. So what do I mean by that? Well, you should observe that the standardization itself is an affine transformation of the variable. You're subtracting something and you're dividing by something. And so if you hand me a linear combination of your standardized variables, I can very easily translate that into a linear combination of your original variables. And so that's nice. Now, there is a fourth reason to do it, and it's one that I don't think is observed very often, and that is to say that standardization, at least in this sense, is idempotent. So what do we mean by idempotent? Well, an operator is idempotent if, when you apply the operator multiple times, you simply keep getting back the same thing. And so a person might say, well, if standardization is good, surely standardizing the standardized variables is even better, right?
Wrong.
But of course, nothing happens when you do it the second time. Why? Because your standardized variable already has mean 0, and so when you subtract it, nothing happens. And your standardized variable already has standard deviation 1, so when you divide by it, nothing happens. Standardization is idempotent. However, a reasonable person might ask, is there any underlying theory of this transformation? And the answer is kind of. And so if you go back to, say, your Stats 101, what you'll remember doing is you would be given a set of data, you would compute the sample mean, you would then go, okay, well, I want to do tests of hypothesis of this. What do I do? Well, I'm going to subtract the mean and divide by the standard deviation. And then I'm going to go in the back of the book and look up probabilities associated with the standard normal distribution. Now, why are you doing that? Well, the answer is because the sample mean, we know from the central limit theorem, is asymptotically normally distributed. That's why you do that. And so when you have a sample mean, you just assume, you act as though it's normally distributed. And therefore, when you subtract its mean, which is the original mean, and divide by its standard deviation, which is the original standard deviation divided by the square root of n, when you do that, you get something which is standard normal, and therefore you can go look it up in the back of the book. And as far as I can tell, those kind of tables go back to at least 1799 from the French mathematician Christian Cramp. So there's kind of an underlying theory, but it's important to realize that there's a difference between a variable and a sample mean pulled from a sample of that variable or computed from a sample of that variable. So to illustrate that, consider the following. So what we're going to do is we're going to look at the probability density functions of both the variable and its standardization. So here on the left, what we have is a normally distributed random variable with mean 100 and standard deviation 10. And so when you take that and you transform it, yes, lo and behold, you still get a normally distributed random variable, now with mean 0 and standard deviation 1. All well and good. But what if your original variable was gamma? So here's a gamma distributed random variable. And so when we take its mean and subtract it and divide by its standard deviation, we get something that looks like this. So same shape, just shifted and adjusted in size. Again, what if you start with a log normal random variable? That's what we have here on the left, and you standardize it, you subtract its mean, divide by its standard deviation. You get something that looks like this. And when you put all three of these things together, what you observe is that although these variables are unit-free and they all have mean 0 and standard deviation 1, they look very different. Their density functions look very different from one another. So in one sense, they're the same, but in another sense, they're like really different from one another, even after standardization, which makes you wonder why it's called standardization if the output is so different. Well, let's try to attend to that problem with the probability integral transform. Now, the probability integral transform is something that's usually associated more in discussions of simulation, but we're going to use it for data analysis. And so here's what we're going to do. For any random variable that you hand me, I am going to hand you back a function defined on the real line called its cumulative distribution function, often denoted as capital F of x. And so basically what you do is, how does this function work? Well, for any real value, little x, you just say, okay, well, what's the probability that my original variable is less than or equal to that? And so we're going to take this real valued function and we're going to compose it with the original variable. And so what's happening here? Well, the original random variable goes from your sample space into the real line, and its cumulative distribution function goes from the real line into the unit interval. And so we're simply going to compose the two to get a function, to get a random variable which goes from the sample space into the unit interval. Now, how does this look in practice? Well, let's take a simple example. So we're going to take a sort of the simplest or second simplest example you can think of, which is just a random variable that takes two values, one at 0, one at 1. But you can think of it maybe as a weighted coin. It takes the value 0 with probability 0.3, takes the value 1 with probability 0.7. And so the masses are indicated on this graph here. Here it is taking the value 0 with probability 0.3 and the value of 1 with probability 0.7. Okay, so what is its cumulative distribution function? Well, if you take any number less than 0 and you say, what's the probability that x takes this value or lower? Well, x only takes the value 0 and 1, so the answer is 0, and that's why you have this blue line at 0 up until 0. Between 0 and 1, inclusive and exclusive, if you say, what's the probability that x takes the value of 1.5 or less? Well, again, the values that x takes, 0.5 or less, the values that x takes are 0 and 1. So that's simply the probability that x equals 0. And so that's 0.3. And so the function takes the value 0.3 on the interval 0 to 1. Finally, if you take something 1 or larger and you say, what's the probability that x takes a value of something 1 or larger? The answer is, well, the only values that x takes are 0 and 1. So the probability that it takes something 1 or larger is 1. And that is why this function here is constant at 1. So that's that. So now we're going to compose the original variable, which takes two values, with its cumulative distribution function. And so how do we do this? Well, if x is equal to 0, then u sub x is equal to f sub x of 0. But we know what f sub x of 0 is. It's 0.3. Well, what if x is equal to 1? Well, okay, if x is equal to 1, u sub x equals f sub x of 1. But we know what f sub x of 1 is. It's 1. And so the original value, the original variable takes the values 0 and 1. The probability integral transform of it, u sub x, takes the values 0.3 and 1. And so this is what its probability masses look like. They're in red here. I kept the original variable on here as well. And so the probability integral transform u sub x takes the value 0.3 with probability 0.3 and 1 with probability 0.7. And so now, because it is a random variable, you can talk about its cumulative distribution function, and it looks like this. And so because it doesn't take any values less than 0.3, it's 0 up to 0.3, and it's 0.3 up until 1, which is its next value that it takes, and then it jumps to 1. It looks like this. And again, I included the graph of the original cumulative distribution function on here. So that's how the probability integral transform works on, say, the simplest case. So here's what we're going to do. For any variable in our modeling data, we are going to define u of x to be that variable composed with its cumulative distribution function. And now we're going to examine the results, and lo and behold, what happens? Well, if my original variable was normally distributed, when I transform it this way, what happens? Oh, I get a uniform distribution out of it. Well, isn't that nice? And here's my gamma. Well, when I use this transformation on my gamma random variable, what happens? Oh, I get a uniform distribution out of it. How about the log normal? Here's my log normal on the left. When I hit it with the probability integral transform, what happens? Oh, I get a uniform random variable. And in fact, you can prove that if your cumulative distribution function is continuous, then u sub x is uniformly distributed. So isn't that nice? Now, in a much clearer sense, everything is the same. They are, in fact, standard, at least when your cumulative distribution function is continuous. But I hear you say, what happens if it's not continuous? What if there is no density function? Reasonable question. So, as we all know, not all probability distributions have probability density functions. However, all variables have cumulative distribution functions. F sub x always exists. And so now what we can say is, okay, fine, let's not worry about the density function because that's not always there. Let's think in terms of the cumulative density function because that always exists for all random variables. Well, it just so happens that when you consider the probability integral transform, the cumulative distribution function of your standardized variable, standardized in the sense of you've used the probability integral transform, it's not that your cumulative distribution function is going to equal the cumulative distribution function of a uniform random variable. It might, if your original cumulative distribution function was continuous. But in the event that it's not, it's going to be as close as possible to the cumulative distribution function of a uniform random variable. And when we say as close as possible, what do we mean? Well, it turns out that there is a way to measure distance between cumulative distribution functions in something known as the Levy metric. And so that is the sense in which the output from a probability integral transform, that method of standardization, gets you as close as possible to a uniform distribution. And so to compare then the two different methods of standardization, this is what happens when you look at the CDFs, the cumulative distribution functions of your normal, your gamma, your log normal, your binomial. I threw in a binomial because it does not have a continuous cumulative distribution function. This is a binomial which has 4 trials and a probability of success 0.25. Obviously, these things are all different from one another. And they're active on different parts of the real line. But now if you compare this mess here with this here, well, here are the cumulative distribution functions of probability integral transformations. And as you can see, it's way nicer. So the first three, because they have continuous cumulative distribution functions, they all have the cumulative distribution function of a uniform random variable. Now, we know that the binomial never had hope of having that cumulative distribution function, but it is as close as possible to a cumulative distribution function in the Levy metric, in the sense of the Levy metric. So, what are the properties of the probability integral transform? Well, again, the new variables are unit-free, so that matches up with the first standardization technique. But here's the key, is that the distributions of the output variables are either uniform or they're as close as you can get them to being uniform. This transformation is also idempotent. So if you apply it once and then you apply it again, you're going to get the same thing that you got the first time. And there's an easy translation, because you can simply go back and forth relatively easily between the rank ordering of the value of the variable and the variable itself. And most importantly, there is an underlying theory of the transformation. And so this is what we are going to use when we do our data analysis. We are going to take all of our predictor variables and we are going to run them through the probability integral transform so that the output, the variables on which we model, are as close as possible to being uniformly distributed as one can possibly get. I hope you found this useful. If you have any questions, please place them in the comments. I am Ian Dieters, and I thank you for watching Full Metal Analysis.
We're all clones, all are one and we're all one.